Hello students, today we'll be learning about one of the very important topics in physics, that is simple harmonic motion. Now, uh, you must have encountered with this phenomena, but you may not realize it right now how it governs. So today our aim is to get a better understanding, a basic understanding about this phenomena. Now, in your daily life, you encounter many actions, many phenomena, but you don't realize their operation. So, let us consider if you throw a rope from a building. Now, once you throw a rope, it will hit the ground and it will remain on the ground forever. Now, this kind of motion is known as singular motion, which only happens once by itself. These are the most general motion that happens in the nature, but there is one more that is very important, that is periodic motion. Now the name itself suggests about its meaning. So there is periodic. Period means repetition after a regular interval. So any motion that repeats itself after a regular interval of time. Regular interval of time is known as periodic motion. Please don't mind my handwriting. I know it's little bad, but if you clearly understand me, if you hear me correctly, you'll understand these topics very easily. So, the example of this motion is pendulum. I'm sure you all have seen a pendulum. So, you all know how a pendulum works. So, a pendulum will oscillate about a mean position, that is known as x equals to 0. We can say equilibrium position. Now the pendulum will oscillate to and fro about this mean position in a regular interval of time, let's say t. Now this is known as periodic motion. If we function it, it will be written as f of t equals to function of t plus capital T. Now this is the instantaneous time and this is the time period of this oscillation. Okay, so I am sure you are now very well aware about the periodic motion. So we'll get into the our main topic, that is simple harmonic motion. So to my understanding, it's best if we learn about this SHM by an example, because you are eventually going to solve many difficult problems. So it's best suited if we go through this topic through an example. So I'll be taking a very simple and a very fundamental example, that is spring mass system. Spring mass system. Now, before we get into anything, let me tell you what exactly are we going to do. So our aim is to, whenever we try to understand anything in physics, in general, we need to know the equation of motion. Not only in this case, but in every case. If you know about the equation of motion, we can know every quantity about related to this quantity. So our aim will be to obtain an equation that governs this motion. Equation of motion, if you can simply say. Then we can find the different relations, that is velocity, acceleration, time. It's very easy if you first find the equation of motion. So we'll be learning about this through an example. So the example being, if you consider a mass m, a block of mass m that is attached to a spring. Now this is a spring. See it carefully. We are going to use this figure very often. Now spring has a spring constant K, and we consider this surface as frictionless. If it's frictional, there will be different forces acting on it, but we are not going to study that right now. It will be a bit complicated. So before we get into frictional surface, we'll start doing it without friction. So you may ask, what exactly is this K? Now the K here stands for spring constant. Now it is a characteristic of a spring. Every spring is different. It has different rigidity. So every spring there is a spring constant assigned, which tells us about its properties. For example, if there are many springs, like you have seen in some toys, there is this kind of spring. I've seen these on fairs. They play with the spring like this is. So it has different K value, and there is this spring that is used in suspension. It can withstand heavy weights. Okay, it has different K. K1 is not equals to K2. So every spring has a different spring constant. So this is the basic that we need to know, and through this we'll be learning about simple harmonic motion. So let me erase this, and I'll get into the mathematics part now. So we are very well aware about the theoretical part. Now we'll be getting into mathematical part. So we considered a spring that is attached to a mass m. This spring was in K. Now what we will do is we'll apply a force F to this mass. What this force will do is this force will stretch our mass, and our spring will be stretched to some extension. Now you can clearly see the spring is stretched. Okay, this is the mass now. This is supposed to be the equilibrium position when there was no extension whatsoever. So this will be x equals to 0. If there is no force, it is known as equilibrium position. Equilibrium position, or I can say equilibrium state, or we can say stable state. On the application of force, our spring will be stretched and it will go x displacement in the forward direction. Similarly, what the spring will do is the spring will create a restoring force, and it will try to regain its equilibrium position, its stable situation. Now, in general, in nature, everything will try to gain its stability. Stability is very important. Okay, so it will try to oppose the force, and it will create a restoring force. Okay, and this FR stands for restoring force. Okay, so on doing so, our spring will also be compressed. Here we are considering there are no external forces, there are no other frictional forces under consideration, so it will go about the same displacement. These can be altered, but we'll be studying about this in later lectures. So if you examine this figure carefully, you can write the force that is restoring is equals to minus k times x, where x stands for the displacement, that is the extension provided by the force, and k is the spring constant, and negative sign indicates that it is a restoring force. It is opposing the motion, it is opposing the force that is applied onto it, so it is known as restoring force. Now if you understand this carefully, SHM motion, simple harmonic motion, has two very basic and very fundamental necessities that must be completed in order to have it in simple harmonic motion. That is, our force of restoring must be directly proportional to displacement, and it should also oppose the applied force, or you can say applied motion. Our restoring force must be opposite to the direction of motion or direction of displacement, and it should be directly proportional to displacement. So these are the very necessity conditions. These are the two necessity conditions for SHF. Now if you understand this carefully, you can also say every simple harmonic motion is a periodic motion, because the motion itself is repeating itself after a regular interval of time. Let's say t time. It will repeat itself after t time. For example, it will go outwards, it will come backwards, then it will come outwards. It will be repeated after a regular interval of time. Now this and this time combined will be known as time period. Okay, I think up to this it's very understandable. So we'll write this as equation number 1. So I'm going to rub this and we'll be doing the further mathematics now. Try to remember, our main objective was to obtain an equation of motion. Okay, so sorry, I have written this equation number 1, that is F restoring is equals to minus K times X. K stands for spring constant, X is the displacement in the spring, and F is the restoring force. Okay, you may put the vector signs. I'm not going to put the vector signs. It's very understandable that these are going to be vectors. So if for your understanding, for the simplicity of our problem, I'm not going to put the vector signs. Ideally, you should always put vector signs onto the vector quantities. It's recommended you should put the vector signs always. But for the basicity of this problem, I'm going to ignore the conditions right now. So now from the second law of motion, you all know F is equals to ma. We can say m times d2x upon dt2. I think you are all aware about this equation. So if we put this into our equation number 1, we can say m d2x upon dt square is equals to minus k times x. If I divide the whole equation by m, it will be written as, and I take the right hand side to the left hand side, we can clearly say plus kx upon m is equals to 0. Now this is the equation of motion. This equation is a differential equation, okay? We are not going to solve the differential equation right now because it will be a bit complicated and it will take some time. We are not aiming to solve a differential equation, but the solution is already provided to us. It's very simple. And today I'm only going to tell you about the solution. If you want to learn differential, how to solve this differential equation, it's very simple. You may refer to your NCERT books, mathematics books. It's already given in class 11, I think. So the equation, the solution, okay, solution of the above equation becomes, I'm not used to writing on the board, so you may have to excuse my handwriting. Okay, so before that, let's let me take a constant, omega square, that is equals to under the root. Okay, before we get into that, okay, so let omega square equals to k by m, which implies omega equals to under the root k by m. This is known as angular frequency. Right now, just remember it. On the further courses, you will understand what does this angular frequency means. Right now, you just remember this. Omega is called as angular frequency, and it is equal to the constant square under root times the constant. Okay. So the solution of this equation is written as, because x is our dependent variable, so x will be a times sine omega t plus phi. Now where a is the amplitude and omega t plus phi is our instantaneous phase. Omega t plus phi is our instantaneous phase, and instantaneous phase, and omega t plus phi tells us about the direction and the position of our object at any instant of time, and phi is our initial phase. It tells us about the initial direction and position. Okay, so we have obtained this equation x equals to a sine omega t plus phi. This is known as equation of motion. What exactly is this? This is the displacement or the stretch or the compression or the decompression in the spring. It is clearly visible. It is clearly seen that x equals to a sin omega t plus phi. If you want to imagine this equation, I'll help you understand this or imagine this equation through an example also. So we had considered our spring as this. Then we applied some force. Our spring will be stretched. Then it will be compressed. Okay. This was the mean position. Now, if you clearly see, if you try to plot the x versus t diagram, what will it give us? First, our block was at the equilibrium position. Then on the application of the force, our block went outwards. Then we can say this is the curve it traces, and it attains the maximum position. Then it comes back to its mean position. That is, comes back to its mean position. Then it will go backward in the same sense. It will go backward. Then it will go to the stable position, and it continues on and on. If you twist this graph, you can clearly see t x versus t is this, something like this. Okay, this is what? This is sine t. Simple. So this can be understood qualitatively also and quantitatively also. Quantitatively we do it by maths, and qualitatively we do it by intuition and understanding our figures. Okay, where were we? We had derived the equation of motion already. Okay, so this is our equation of motion. Let's name it as equation number 2. Now if we derivate it with respect to time, we'll get velocity dx by dt, which will be equals to a omega cos omega t plus phi. This will be velocity, and you can say calculate acceleration also, d2x by dt2. It will be equals to minus a omega square sine omega t plus phi. Okay, acceleration has minus sign, it tells it opposes the motion of our displacement. Okay, so if you further want to calculate or further want to understand this problem, it will take some time. For today, we are going to end it here. But in the further lectures, we'll be understanding more about this, and we'll be solving many difficult problems about this. Okay, thank you.